Hello friends, the topic is Introduction to Clean Room Software Engineering. Here, the process of developing the software using formal methods instead of classic analysis, design, code, and testing cycles. This method is used to build most reliable software. This method was developed by Harlan Mills at IBM. Steps. Number 1, write the code correctly first time. Second, verify the correctness before testing. Using this method, software is built such that rather than identifying the defect, introduction of defect is avoided. Prevention is better than cure. Specialized version of incremental process model. Here, software is developed in the series of increments. The critical functionalities are added in early increments and less important functionalities are added in later increments. Second one is that according to change in customer requirements, new things may get added or existing things may get removed. From the released increments, increments are tested. The clean room process model. Friends, this is nothing but the clean room process model where different types of keys are used and the actual presentation or actual diagram clears the whole process of clean room where key processes, work products, processes and work products, these are the two keys used in this process where there are very much customer requirements which are specification function usage. Goes to the next, that is incremental development planning, which is divided further into two: box structure specification and design correctness verification, and second one is usage modeling test case generation. Here the incremental development plan is driven and these both are again combined in statistical testing where failure of data sometimes may occur and give the last quality certification model where measure of operational performance are carried out. Here source code and test cases are used for combining these two boxes for statistical testing. The improvement feedback is carried out. Friends, here the clean room process where many activities are carried out in step-by-step format and all are connected to each other through the diagram. Where first activity, that is customer requirements, where requirement specification and usage specification, customer requirements are divided into these two and these two again are combined in incremental development plan where output of these two is input to incremental develop plan and goes further dividation, that is incremental design and documentation. That means incremental development plan is divided into design and documentation. In the design process, correctness and verification. For that purpose, we are using the decision blocks. If there is a correctness and verification carried out, yes, no conditions are carried out. If yes, then go to the statistical testing. If no, then again go to the first step and process will carried out from first to last. That means incremental design. Suppose correctness or verifications are carried out, yes, go to the statistical testing and certification model. Again, we have to check it is certified or not. If certified, then go to the incremental certified system. If no, then again go to the previous process and further process is carried out up to the certified model. These are the steps in clean room approach are formal specification, second, increment planning, third, requirement gathering, fourth, box structure specifications, fifth, formal design, six, correctness verification, seven, code generation and inspection, eight, statistical test planning, number nine, statistical use testing, and last one is certification. In the formal specification, the software to be developed is defined using a formal method. In second, increment planning, according to customer requirements and priorities, increments are developed and delivered to the customer. Each increment must be validated separately using clean room process. These increments must be integrated time to time. Specifications. Here, two specifications are produced, functional and usage. In the functional specification, it defines the required external system behavior in all circumstances of use, forms the basis for incremental software development. In the usage specification, it defines usage scenario considering user, person, hardware device, or other software subclasses may exist. Use a particular work session or transaction bounded by specific start and end events, environment platform, OS environment, system load, etc. Forms the basis of statistical testing and quality certification. Incremental development planning. Here we are planning the increment. First one, development. In that we are taking number of increments, that is 1, 2, 3 up to n. In the testing and certification, these increments are tested and certified, and finally the configurations are carried out. Incremental development. Requirement gathering. Here, customer requirements are gathered and analyzed in this phase. In the fourth, box structure specification. Specification methods in which box structure is used to describe functional specification. In this kind of specification, at each level of refinement, the creative definition of behavior, data, and procedures are separated out. Here, the box structured design. In the box, structures are used to systematically move from an abstract specification to a detailed design providing implementation detail. This is design of structure, box structure. Box structure model. There are black box, state box and clear box. These are the models. First, black box gives an external view of the component, provides a description of functional requirements without details on the internal structure and operations, describes the user visible system input and responses. State box gives an intermediate view of the component, decomposes the black box into an internal state representation and an internal black box. Clear box gives a detailed view of component, replaces the internal black box with a detailed design using structured programming constructs. This is the box structure development. System development is a process of stepwise box decomposition. This is nothing but the box structures. Stimulus, black box response. Box structure. Here, stimulus as an input and black box. There are many block box and response is an output. Block box structure principles. The behavior of black box is same regardless of where in the system it is referenced. The implementation of a black box is independent of implementation of other part of system. Referencing a black box is equivalent to referencing its corresponding clear box representation throughout the system. For example, 7 cloud be substituted for 5 plus 2, 7. Transaction closure ensures that a sound and complete set of transactions is identified to achieve the required system behavior. Black box level system stimuli are necessary and sufficient to generate the required responses. State box level defined transactions must be necessary and sufficient for the acquisition and preservation of all state data, and the state data must be necessary and sufficient for the completion of all transactions. Clear box level procedural design and the internal black boxes must be include all transactions. This is box structure principles where state migration state data should be stored at as low or level as possible, but as high as necessary for expedient downward migration. As new black boxes are created in a clear box, any state item referenced slowly in a given black box may be migrated downward into that black box. In upward migration, when state items are duplicated in several places, it can be moved to the nearest common parent. Common services. Reusable boxes may be created or referenced from a library of reusable components. If from a library, the common service is pre-certified, component can reduce system size and complexity. Formal design. Increments are converted to component and architectural designs referred to as box. Architectural level design is called state box and component level design is called clear box. 6. Correctness verification. In that, the rigorous verification is carried out on design and then on coding. At the first level of verification, the set of correctness questions are used. For more rigorous verification, formal or mathematical methods are used for verification. Correctness verification. The procedural control structures of structured programming are single entry, single exit structures, thus producing no side effects in control flow. When it executes, a given control structure simply transforms data from an input state to an output state. This transformation is called as the structure's program function. This is the example. Correctness verification. In designing clear box procedures, you define an intended function, then refine it into a control structure and new intended functions. Intended functions are recorded in the design and attached to the corresponding control structures refinements. So, clear boxes are composed of a finite number of control structures, each of which can be checked for correctness against its intended function. To verify the correctness of each control structure, you derive its program function. A correctness theorem formally defines how to do this for each control structures in terms of language independent correctness conditions. This is the correctness verifications example. Correctness verification during the team review. Every correctness condition of every control structure is verified in turn. Each team member must agree that each condition is correct. Thus, an error is possible only if every team member incorrectly verifies a condition. If an informal approach cannot produce a unanimous decision, formal proofs of correctness can be employed. This is more efficient and produces better code than unit testing. Visual aids for verification. Code generation and inspection. The box structure specification is translated into programming language. The correctness of the code can be tested using walkthrough or inspection techniques. Finally, correctness verification is done. Last one is statistical test planning. The suite of test cases is designing for a statistical testing. With this test planning activity, the clean room activities such as specification, design, verification, and code generation activities are conducted in parallel. 9. Statistical use testing. A series of tests are conducted. Statistical testing. Testing software according to the way users intend to use it. The entire focus is on external system behavior, not the internal of the design or implementation. The certification team's goal is not to debug but to certify the software's quality. This requires deep knowledge of expected usage but no knowledge of design or implementation information. Last one is certification. After completion of verification, inspection, and use testing, the increment is certified. This increment can be integrated. Based on the data gathered during statistical testing, the software can be given a certified reliability. Reliability is expressed as MTTF and is computed according to specific mathematical reliability methods, models, sampling model, component model, certification model. Merits and demerits of clean room engineering. Merits are the zero defect software can be developed. Defects are discovered and removed during early stages of development. Cost effective static verification is carried out. And the demerits are the formal mathematical proofs required to check the correctness of programs. Developing such proofs is very expensive. It also requires knowledge of mathematics and formal semantics of program. These are the approaches. Clean room SE differs from conventional and OOSE because of following reasons. Clean room approach emphasis on statistical quality control. Mathematical proofs or formal methods are used to verify the design specification. Errors are uncovered by testing techniques. Thank you so much.